So I've been involved in operating networks since 1995. I'm sure there are some people in this room who weren't born then. So I started working for an ISP. The first year the internet was commercially available in the United States. Before 95, it was academic and government only. And since then, I've been working in and around networks, IP networks, in a number of different ways. For the most part, recently in wireless. So I started playing with wireless in 1998, and by 2003, I had started a business in New Zealand. I went to New Zealand to get a master's degree in information management, and the internet in New Zealand was terrible. I've lived in Boston before. So I dropped out of my master's degree and founded a wireless company and spent a number of years building that company until I sold it in 2011. That company provided wireless connections for ISPs. So it was a carrier for carriers, providing wholesale only Ethernet connections over wireless. And even then, in 2006, I was using some technologies that were quite new, like millimeter wave. People speak about millimeter wave as 5G, but we were using 60 gigahertz for broadband more than 10 years ago. Anyway, all of this wireless has led me to a real interest in satellite, because the next generation of satellite networks is all basically broadband microwave in the sky. So we start. Why do we need broadband in the sky? Here are a few of the points that we're going to cover, but really today I want you to learn some language. I want you to learn 3 frequency bands that telecommunications operators use, not science operators like we were hearing yesterday and the day before. So 3 satellite bands for telecommunications and 3 orbits that are common for telecommunications. Yesterday we heard about some eccentric low Earth orbits, and we're going to talk about very regular low Earth orbits, very regular medium Earth orbits, and geostationary orbits. So, why do we need broadband from the sky? What are the problems with distance and latency? Importantly, what radio spectrum are we going to use? And what happens with rain fade? What about the speeds, the architectures, and the resilience of satellite networks, and why do we care? So, why we care is very easy. I've adjusted this deck for Chile. So, yeah, sorry, I'm not used to people playing with their phones while I'm speaking. So I've adjusted this deck for Chile, and this is a diagram made by Communications Research Canada around 15 years ago. And it has the relative cost and complexity of building an access network compared to the population density. So here we have 0 to 100. Here we have population density of 0.1, 1, 10, 100, 1,000 people per square kilometer. Where I've been staying in the Philippines recently, we are at more than 15,000 per square kilometer. Up here, I'm afraid the projector isn't giving us a good red. For some reason, we're not getting a red at all. So this is a fiber optic network. And when you get to around 3,000 people per square kilometer or more, fiber optic networks are the least costly and complex option of all technologies. As you get lower and lower density, You have technologies like DSL, cable modems, that's DOCSIS, if anyone knows telecommunications, cable modems, and then fixed wireless. Fixed wireless could also be mobile wireless these days, because most people in the developing world are using 3G, 4G for their broadband. So, Santiago, what, like 400 or 500 people per square kilometer? It's actually not a very dense city, not the region as a whole. The region as a whole here, Valparaiso region, just over 100 people per square kilometer. In these areas, the least complex and least costly technology is going to be cable modems, using the cable TV network for broadband in Valparaiso. And I'm looking at, sorry, it's going to be fixed wireless for Valparaiso and fixed wireless or cable modems for Santiago. You want to be at the bottom of the curve, the least costly and complex. But then when we get out to Chile as a whole, just over 10 people per square kilometer, satellite. You get to the region to the south of here, I send 1 person per square kilometer. Does it make sense to build some terrestrial access network for ISEN? No, it doesn't. Satellite is the best option. Now, today, these curves have changed because of new technologies like LTE, upcoming 5G in UHF spectrum, some things called TV white space. There are telecommunications technologies that pull the curves out, but nothing is going to handle 1 person per square kilometer in a more efficient way than satellite. So this is the why. Easy. Why not? So this idiom is more appropriate in America or Australia because people really, especially in Australia, people really like their cars, their fast cars. I guess America is the same way. When people go to buy a car, they buy horsepower, but when they put their foot down, it's not horsepower that's moving them forward, it's torque. Similarly, when people buy broadband connections, they buy a speed of megabits per second, or maybe they buy a gigabytes per month, but that's really not their experience with the broadband. Their experience is driven by latency. All humans notice latency. This is a set of 41 million samples of a psychology experiment or a coordination experiment where you see something on the screen and you click your mouse to say, I see it, I see it. The median reaction time of 41 million samples, let's see if I got this right, is 279 milliseconds. Half of all people react within 270 milliseconds. Half of all people will notice something that's slower than 270 milliseconds. When you get out to 320 milliseconds, that's most, 2/3 of people are going to notice that it's slow, it's something slow. We used to have satellite connections to talk on the phone. And when I was at university in the 90s, I would speak with people in the Middle East, and there would be a 1 second delay sometimes. We'd speak, and then we'd wait, and then we'd speak, and then we'd wait. And sometimes we'd speak at the same time, and then we'd both back off, and then we'd both try again. And someone had a poster out in the poster sessions about Max for satellite. This is a collision avoidance problem. Anyway, Satellite broadband has generally been terrible because for the last 15 years of satellite broadband, everybody's been using geostationary satellites. Now I took that same reaction time curve and I plotted it here quite nearly to scale. My Earth is to scale, my distances are to scale, and my satellites are at about 500,000 to 1 scale. You wouldn't see these. You wouldn't see these satellites here. So, 480 milliseconds is the minimum to get a signal from a user up to a satellite, down to an Earth station, and then back. But it's worse than that. Made a new chart here. Is that the one? There's no red. There's absolutely, like, the red color is completely gone. So you're missing, you're actually missing words and data here, which is bizarre.
Because there's a pin gone or something, or a bulb out. Crazy.
Well, I'm very sorry, but you're just going to have to imagine the arrows here. The way this works is, here's my end user, here's my geostationary satellite. I'm going to make a request. It's going to go up to the satellite. That's going to take 120 milliseconds because speed of light, 36,000 kilometers, 120 milliseconds. We're going to go down to the Earth station. And then from the Earth station, we're going to go across the internet. And the internet's latency is variable. If that Earth station is here in Santiago, and the information you need is in Europe, this may be another 300 milliseconds on top of your 480. It could be more. And the way internet protocols work with TCP is you have some setup of connections, you have some exchange. With web pages, you typically grab a resource and then it points you to 20 other resources on a number of different servers. If you load an English newspaper, I use the Daily Mail as a bad example, you may be connecting to 40 different servers, mostly for advertisements. So, up, down, out. Now, here's that human reaction time. Everyone is noticing that it's slow by about here. Here we are, and then we're adding 300 milliseconds. Desperately slow, terribly slow. It feels slow, and no one wants to use geostationary satellite for internet, but millions of people do. One good thing, geostationary satellite, for streaming, once you start a stream, it just keeps coming. So if you want to watch YouTube, you want to watch Netflix over your satellite internet, that's going to work great. You want to play a video game, have a Skype call, that's not going to work great. Okay, so satellite is slow. Game over. Let's step back from these statistics and start learning about the technologies. And then maybe you'll get excited about what's going on. First, none of you know this. The other places I've given this talk, I've always known at least 10, sometimes 50 people in the room. And they all know that I'm a radio person. I spend most of my time doing radio and wireless. Anyway, a few things about radio here. The pluses of radio is that waves in the air travel at nearly the speed of light. And that is 40% faster
than through fiber optic cables. It's also faster than through copper cables. You have a velocity factor through copper that is much lower than the speed of light. Now, a negative thing about radio waves is that things in the air can attenuate waves. Reflect waves, absorb waves, cause them to not get from point A to point B. Things like rain, snow, birds, yes. Swarms of locusts, absolutely. Elon Musk, maybe, with his jetpack. Now, a neutral thing about radio is that different frequencies have very different property waves, and bigger waves behave differently from smaller waves. We'll go into that in excruciating detail. Now, the three terms, I wanted 3 terms about radio spectrum and 3 terms about orbits. The 3 terms for spectrum are C-band, Ku band, and Ka band. And over the last 2 days, we also heard X-band, which I think was referring to about 12 gigahertz. We heard S-band, which was down below C-band. These other bands are narrowband or dedicated to science or research. They're not available for telecommunications. The telecommunications satellite bands that are important are C, Ku, Ka. Excuse me. So C-band is this big swathe here. And to give you an idea of how much spectrum, I put Wi-Fi, 2.4 gigahertz Wi-Fi is this tiny little streak right here. There's all of 83.5 megahertz of spectrum in the 2.4 gigahertz band in most countries. Get up to the 5 gigahertz band and you have a few hundred megahertz right there. There's more spectrum available for 2G, 3G, 4G. That's in and around here. When we get to 5G, it's 2018. So next year, the ITU will have a World Radio Conference where they determine the spectrum bands for 5G. I expect that there will be some more spectrum around here, in particular 1.5 gigahertz, 600 megahertz. Then I expect we're going to have some Ka band spectrum dedicated to 5G. I expect. That's next year. For the time being, the only thing we have up here is satellite for communications and point-to-point microwave. So here's C-band, here's our Wi-Fi, here's Ku band from around 12 to 18 gigahertz, and here's Ka band from around 26 to 40 gigahertz. Notice that Ka band has a lot more spectrum than C-band or Ku band. Now, I should also say that there are lots of spots in C, Ku, and Ka that are used for other purposes, depending upon the country. So it's not like you have all of the spectrum to work. So here is our quick and easy chart. Holy cow. There's no red. This projector has no red. So imagine this is a gradient of red to green. I'm so glad that I've got these shapes here too. Dang. Anyway, we have C-band down here, a very small amount of spectrum availability, a very small amount of spectrum reuse, very large antenna sizes, and very little rain fade. here we are at 3 gigahertz along the bottom, and then I've taken it all the way out to about 42 gigahertz on the right. Now over here at Ka band, we have a lot more spectrum available. We have a much better spectrum reuse. I'm going to go over these terms in next slides. We have much smaller antenna size, and we have much worse rain fade. Let's look at reusability. This was the picture of Australia in my last talk. I've taken Chile, and I'm sorry, you have to rotate it a bit to fit it on the screen. Reuse is taking the same frequency and sending it down from a satellite multiple times in different places. Here, our C-band coverage is huge. The great thing about C-band, huge coverage. The bad thing is that here's your one small block of radio spectrum, and you've set it across this entire population area. Whereas a similar size of KU spectrum, because the waves are smaller, the antennas are smaller, you can get a higher gain antenna in a smaller space. You can reuse the same KU band spectrum a number of times. Ka, even better. KU band has approximately 4 times the reuse factor of C, and Ka band has approximately 16 times the reuse factor of C. I'm going to show you this in more practical terms with a new satellite that the Brazilians put into service last year. This is satellite SGDC. I don't know what that means. But I went to a great website called satbeams.com, and they show you where the satellite is broadcasting. And in this case, this little circle is number 60 spot beam of 67 Ka spot beams. Now, the best broadband communications satellite covering Brazil before this, I think, had 4 or 10 spot beams of KU. Here we have 67. They cover their entire country, and this satellite is just for government and military networks. I expect they'll be providing broadband to schools, broadband to local government offices on this satellite. So, 67 spot beams from one satellite. What do we got? Satellite antenna size. So I've made a diagram here showing a few different satellites, all of the same gain. So gain is this ability to focus energy, to focus radio waves. Think about a light bulb. If you have a light bulb, you take a reflector, you put the reflector behind the light bulb. You don't create more energy. You only take light that was being reflected back and you move it in one direction. Antennas never make more signal, they only focus the signal that's already there. So for a C-band antenna, to get a 30 dBi gain, that's a dBi is isotropic decibels. It's a comparison to a perfect isotropic antenna, one that's radiating energy in 360 degrees evenly. Like the sun. The sun is radiating evenly in all directions. So, to have a 30 dBi antenna in C-band, it's probably 1.2 meters across. In the KU band, it's only 600 millimeters. And in the KA band, it's only 300 millimeters. I know you can walk around this town and you can see C-band antennas on the ground with concrete pads and big steel posts. And these antennas are covered in moss because it's winter here all the time. It's dark and cloudy. Where did the sun come from anyway? I was really surprised to see the sun this morning. C-band antennas are inconvenient. They're big. They're really big. And yet, KU band antennas, you see them on top of buildings. You see them on balconies. You see them everywhere because people use KU for television. KA band, even tinier. Now, let's think about being out in space, and we have a power budget of 1 watt of electricity for our transmitter from the satellite. If we stick a 30 dBi antenna, 1.2 meter antenna, 30 dBi at C-band, we're on the satellite with a 1.2 meter antenna, we get an effective isotropic radiated power of 1,000 watts. Yes, if you have 1 watt and a 1.2 meter reflector at the focal point, you can cook a chicken. It is actually a microwave. You will cook things with it. 1,000 watts. But if you use the same size antenna at KU band, it's 4,000 watts. And if you use the same size antenna at KA band, it's 16,000 watts. The chicken will be burned. So these are very striking figures. With the same size dish, you get 16 times the power between KA band and C band. So KA band wins. We only use KA band from now on. It's smaller, there's more bandwidth, it's faster, it's just perfect except for rain. So, higher bands mean more rain fade. And this is a section that I added yesterday because it's quite important for people in Valdivia and people in Reyes? What was the far south? What was the name of the province of the far south? Aisien, that's it. Thank you for Aisien. This one. Look. Broadband satellites in geostationary orbit and medium Earth orbit are all sitting above the equator. So if you are on the equator, you're pointing up, you're going through a little bit of rain. How much rain? 2 kilometers, maybe 3, 4, I don't know. If you're down here, you have a low look angle, your satellite's like over there, you might be going through a lot more rain. Now, rain is not consistent or static. There's no red. There's no red. Just imagine, this is red right here. This black, this absence of light here is our red. This is a rainstorm in 3 dimensions. This is ground level, this is 6 kilometers up. We have a little bit of rain coming all the way from 6Ks. We've got most of it concentrated in the 2 to 3 kilometer coming down here. And look what's going on. If we're pointing straight up here, we may not have any rain for a moment, but this is moving. You know that rainstorms move. So as the storm moves, you get varying rates of rain. you have a varying amount of rain you're going to go through. This, by the way, is a 3D view inside of an extratropical cyclone off the coast of Japan in March 2014 by the GPM's dual frequency precipitation radar. And the credit for this is JAXA and NASA. I put a link down here to an article that's really worth reading. So I'll put these slides up for download. Click that. If you want to see rain, click that link and read more. So rain is not consistent or static. Lower look angle equals more rain. And now higher bands equal more rain fade. This chart has frequency in gigahertz along the x-axis here, starting at 3 gigahertz and going up to 100. Oh, I was getting creative. Okay. 3, 5, 10, 30, 100. Some log function here. I made this chart last year, so I'm having trouble remembering. Here we have the y-axis, attenuation in decibels per kilometer. This is 1/10 of a kilometer, sorry, 1/10 of a decibel, 1 decibel, 10 decibels, 50 decibels right there. Here's our bands: C band, KU band, KA band, and B band. Put that off for a moment. C, KU, KA. And over here with these lines in our second y-axis, we've got a drizzle and a light rain. I think the base state for Valdivia is somewhere between this drizzle and light rain. I think that's the normal. Then we have a medium rain somewhere between 2.5 and 12.5 millimeters per hour. We've got a heavy rain at between 12.5 and 25 millimeters per hour. And then we have a tropical downpour at 50 millimeters per hour. I don't think there are any tropical areas in Chile, but as I said, I've been working in the Philippines, and getting a tropical downpour is something that happens every day, basically. Throughout the rainy season, you'll wake up, it'll be nice and sunny, go through the day, gets to about lunchtime, 1 in the afternoon, boom, the rain comes down. By about 3 o'clock, it stopped. Really weird. Anyway, so C-band, decibels per kilometer. It's a lot to keep in your head here. One more thing to keep in your head. The fade margin, the amount of excess signal that you have on a satellite link, is usually 5 to 10 decibels. Why is it not more? To get more, you either need more power from your satellite, which is extraordinarily expensive, or you need a bigger dish on the ground. Most people do not want big dishes in their gardens. They don't want a 1.2 meter C-band dish sitting in their front yard, or bigger. Me, I love antennas. I have any size antenna I want. Doesn't matter to me. Not normal. So, 5 or 10 decibel margin for the rain to take away before you start having problems with your link. C-band. C-band, tropical downpour. This is a likely one for tropical markets. We're losing like, at the top end, we're losing like half a dB per km. Here's our storm here. In all honesty, even if we've got a really bad look angle here, we may be going through 8 kilometers of rainstorm. That's 4 decibels that we've lost. We're still within our link budget for C-band. For KU band, it's a bit different. Here's our tropical downpour. That's somewhere between, say, 3 and 5, probably closer to 3 decibels per kilometer. So, yeah, if you're not lucky, you can do pretty badly with a KU band link. And you know these rainstorms move, and we're not getting rain all of the time, so really the total of this might be a bit less. So we may be okay most of the time with the KU band link, but not all of the time. Then we get to a KA band here, where in this tropical downpour, we are losing a minimum of 9 decibels per kilometer. Possibly 10. Our link budget is gone as soon as it starts raining. It's pretty bad. We're not talking about hurricane-type rains, which are up here. Hurricane Harvey in the United States last year, 96 millimeters per hour of rain. That would take out almost anything. So, C-band just keeps going. KU band may have some interference. KA band, it's just gone. Look back to what the Brazilians did here. 67 KA band spot beams. Do they get tropical rain in Brazil? I think so. I haven't been, but I would assume they do. Okay, again, this is one to feel free to download. The chart is actually an amalgam of, these are ITU rain rates, so you can get these at itu.int. I've just flashed them up a little bit, and the rest of the chart's mine. So, here's a straw man. Here's a comparison of the various technologies and what you might do with them. Remember I said there's very little C-band spectrum compared to KU and KA? On a C-band connection with a 1.2 meter dish on the ground, you might get a 16 megabit per second throughput at a particular cost. Say this is at a cost $1,000 a month. You might get 16 megabits per second at 99.995% availability. In KU band, you probably get 4 times as much. You're down to 99.9% availability. And in KA band, 512 megabits per second at 99.7% availability. What does this mean? It means that 0.3% of the time is basically every time the rain starts coming down heavily. So you're going to have your storm at 1 o'clock in the afternoon. It's going to start, your service is going to start fading as the storm cells move across. The heavy bits are going to cause your service to go down. It's going to go down for 10 seconds, 20 seconds, then it might come back. It's going to go down for a minute or 2 minutes, and then it might come back. You're going to have an hour of misery during this storm. Because even though some of the packets are going to get through, the way we have designed telecommunications networks is incompatible with packet loss. Completely incompatible. So while this rate may say 99.7, it's going to suck. The funny thing is, a lot of people in governments, especially in the Pacific, don't believe that 99.7 is bad. They think it's good. And so a few companies have sold multi-year contracts to Pacific Island governments on satellites that haven't been launched yet. They've sold them based on 99.7% availability. The one government that's done a trial for this Ka band service has found that it's pretty shit. And they stopped using it. Yeah. So, Ka band. It seemed like it was the best, and now it seems like it's the worst. What do you do? Oh, by the way, you can get better than 99.7% availability on Ka band. You can even get 5 nines. You just need a really big dish. And when I say really big, I mean like 7 meters. We have some other tricks for fixing the Ka problem I'll discuss in 2 slides. Right. Let's go on to architecture. The green, oh, I didn't use red in this diagram for me. The green ball up here, I used orange. These are actually orange on my screen. Green ball is our satellite. The big box is an Earth station. The little box is a subscriber. Here we have our standard geostationary go up, come down. You know that means go up, go down, go out to the internet, get our data, bring it back, go up, go down, freaking slow as. There we go. Now we have this idea that we might do redundant VSAT. Why? This link right here, if this is in Hawaii, might fade sometimes, even with a really big dish. There is an Earth station run by Intelsat in Oahu that has terrible rain fade problems. So if you're anywhere in the Pacific, you're using this Earth station, you might find that, well, your link is just fine, it's not raining on you, but your service isn't working. So you might want to get 2 VSAT connections. And I know Pacific Island operators who've used up to 4. That example was Solomon Islands Telecom, called our Telecom. And they had connections to Australia, Hong Kong, Guam, and Los Angeles. 4 different satellites coming down in 4 different places. So, redundant VSAT. You take care of linking the Earth stations if you want to have a fail-proof service, or you just treat it like internet connectivity as the Solomons did, and they connected via BGP with the global networks in 4 different places. This is a bit more interesting. This is the idea of using 2 different orbits of satellite. Now this may be a medium Earth orbit satellite service. This may be a geostationary satellite service. This is happening. This is happening throughout the Pacific now because people have found their Ka band medium Earth orbit service has terrible rain fade problems. And since they spent $250,000 building the base station for it, they said, well, we better supplement it with something. And generally, that something is a geostationary C-band. So here we are, fiber linking the Earth stations, 2 different satellites. Now finally, we have a configuration that was in use in American Samoa until 3 months ago, and is in use in Papua New Guinea today. And this is satellite plus fiber optic. The reason is the fiber optic cables that were connecting Papua New Guinea and American Samoa, the cables themselves had no problems, but the repeaters every 60 kilometers under the sea were constrained to around 1.1 gigabit per second of capacity, non-upgradable, because they were taking an optical signal, converting it into an electrical signal to amplify it putting it back into the optoelectrical system. E5 capacity, really gross time division multiplex stuff. Old, so they're stuck with a reliable, low capacity fiber and quite an unreliable, high capacity satellite service. And it's worked out okay for them because they can decide what kind of traffic do we need, high reliability, that is payments, banking, electronic transactions. What can you handle with unreliable? Email. Absolutely email. If email doesn't send from one server to another, it just waits a little while and tries again, which is fine. Now we have some advanced architectures, and the second one is really cool. The first one, we're not doing much of now, but we will be in the near future. That is, signal goes from a terminal up to a satellite and across, and hops from 1 to 2 to 3 to n satellites. This happens today and for the last 20 years with a voice and low-speed data network called Iridium. The Iridium network has used satellite cross-linking forever. If you're interested in satellite, there's a book about Iridium called Eccentric Orbits, the Iridium Story, and it has the technology, the politics, and the commercial backstabbing involved. I think a lot of the politics was backstabbing too. It reads like a Tom Clancy novel. Serious political intrigue. Really, really interesting. So that's Eccentric Orbits, the Iridium Story. Anyway, back to this satellite cross-linking. We do not have data, broadband data services today that use satellite cross-linking. Everything we have is up and down. That will change any month now. What we've been doing for Ka-band is seriously interesting. Now, the first Ka-band, commercial Ka-band broadband service for carriers started in 2014 with a medium Earth orbit network called O3b. O3b was going to be the savior for islands around the world. And O3b went in, and everybody's like, this is amazing, the cost is low, the speed is high, and oh no, it's raining shit. Terrible performance in the rain. And so what did people do? They started building bigger antennas on the ground, and it wasn't helping enough. What they decided to do was take advantage of this. The fact that rainstorms are never consistent, and in island environments, especially where there's a mountain in the middle of the island, this happens more often than you think. They find that one side of the island may be dry, while the other side is pouring with rain regularly. So, in the first configuration in the Cook Islands in Rarotonga, O3b built a free second Earth station for Telecom Cook Islands because my friend Adolfo, who was the CEO there, was trying to kick them out. He really, really was very angry at O3b because their Ka-band service was so unreliable in the rain. So they built a second Earth station on the island. They linked them with fiber optic, and what do? But look at the receive levels at the two dishes from the satellite in real time and decide what has the better signal. He's the one with the better signal. They're connected by fiber optic. I mean, the delay is basically nothing. It's a few kilometers or tens of kilometers. I've walked from the north to the south of Rarotonga over the mountain. It only took like 2 hours. So It can't be that far. A couple of Ks. After being successful in Rarotonga with this strategy, they've repeated it in the Solomons. They've repeated it in, I think, in PNG now. Dang. I've been told that this is now a standard configuration for O3B Ka-band service. Just build 2 sets of antennas, put them in different places, run fiber between them, choose the best signal. Nobody thought of doing this 5 years ago. Like nobody. Like why would you do that? Just build a bigger antenna. But it turns out that Ka-band is so affected by the rain, this is a legitimate strategy. So that is it. Not only is this a legitimate strategy, but it's one that's been used or might be used on a really cool network that I'll talk about in a few more slides. Great. Orbits. We had our spectrum. Remember our spectrum: C-band, Ku-band, Ka-band. Now we get to our orbits: GEO, MEO, and LEO. 36,000 kilometers, 8 to 12,000 kilometers, anywhere from like 400 to say 1,200 kilometers up here. So for GEO, we the human race, have been doing telecommunications in geostationary or geosynchronous orbit since 1965. And the first satellite there was Intelsat. To get coverage of the world, most coverage of the world, you need 3 satellites. I say plus or minus 82 degrees, because guess what? 36,000 kilometers, you've got this round Earth thing. If you're beaming down, you still don't get the North Pole, which doesn't exist anymore, or the South Pole. You don't get Antarctica from GEO. For GEO, you get stationary receiver dishes. Point them once, aim them once, don't touch them again until the earthquake, and you have to reform them. We had a 6.7 earthquake in New Zealand yesterday. All my friends have been posting pictures of them. Scared, but nothing broken, so yay. Geostationary orbit is mass market satellite. We've been using it first for voice communications, then for broadcast television, broadcast radio. Satellite TV is a thing. Satellite broadband has been a thing since, I guess, 2000, 2003. The first real mass market satellite broadband was coming out around 2003, 2004. This particular satellite, owned by Optus, which is an Australian company that is part of the Singtel group. If you're a telecommunications carrier, this stuff is way more interesting. Anyway, they have this satellite at about 152 degrees east, Ku band, and the type of service that they're providing, this is a New Zealand company providing a broadband service to New Zealand. They can get on their channel, on their Ku channel, around 540 megabits per second as a downlink. The user terminals can receive a stream of up to 16 megabits per second and can send a stream of around 2 megabits per second. It's quite hard for user terminals to encode and send information that's going 36,000 kilometers. You know, the satellite has a lot of power behind it, but can you imagine sticking like 1,000 watts into your set-top box to make your internet work? No, it'd be like a heater. Most people's satellite modems are taking 100, 150 watts of electricity. If they're really efficient, maybe 50. So you only get a small amount of encoding data sending it up with this. This is an old style service. This was servicing at peak in New Zealand around 15,000 users. 540 megabits per second divided by 15,000 users equals shit.
Oh no.
It was terrible, so slow. Now the solution for that came from the Australians, who in 2016 launched 2 of these satellites. Look at these people here. That's a freaking huge antenna. It's like 4 gigantic. I don't even know how big they are. These guys are like 2 meters tall, so these are like 4 meters or something. You wouldn't want to stand in front of one of these antennas when it's going. Definitely not exist. It would be smoking. They planned this service to run from 2 years ago until 2030. Geostationary orbit, Ka band, so in the far north of Australia where it's tropical and it rains all of the time, people hate this service. But in the rest of Australia where it's so dry, it catches on fire spontaneously. People are fine. Some parts of Australia are really, really dry. You know, they don't get rain, and when they do get rain, nobody's on the internet. They're all outside saying, hey, it's raining. So, to handle this, Australia's National Broadband Network Company built 10 Earth stations. They've got a 135 gigabits per second of capacity to share between their hundreds of thousands of users. End users are getting around 25 megabits per second down, 5 megabits per second up. They have designed this service to be upgradable with higher modulation user terminals so that people will soon have 50 megabits per second down, 10 megabits per second up. This makes for happy broadband users when it's not raining. Unfortunately, it is not practical for home users to build 2 antennas connected by fiber 10 kilometers away from each other to avoid the rainstorms. So, for the people of Darwin, Australia, which is in the far north, for the people of tropical North Queensland, like Cairns, if they need to be on satellite like this, for the time being, it's just going to suck. Sky Muster. Oh, come on, clicky. Did I break it? I haven't even been using it right. I've only been using it as a laser pointer. Silly. One second. Much better. Okay. Now, that's geostationary orbit. And the coming back to this guy, SGDC, this is geostationary orbit. If you go to satbeams.com, each one of these little things here is a satellite, and this is degrees, so like you can hover over. Actually, this satellite is sitting here above the top of the roof. You can click through and see which satellites are where they're beaming their information down. Most of what has happened in the last 10 years, almost all, has been geostationary. But the interesting stuff is happening in medium Earth orbit. Our first medium Earth orbit network ever launched in 2014. And this is an FCC filing, because any satellite company that wants to have a satellite that has anything to do with US airspace basically has to get approval from the FCC to do anything. So, a medium Earth orbit network means you're going to be out here between around 8,000 and 12,000 kilometers, and I've lied to you already. Medium Earth orbit has been around since a lot longer than 2014. Medium Earth orbit for broadband has been around since 2014. Before 2014, we had lots of medium Earth orbit satellites for GPS. GPS, Galileo, GLONASS, Baidu, all of these networks are medium Earth orbit. We also have things like spy satellites, weather satellites, cameras, flying cameras, whatever. Not broadband internet. Network operators like me, we just care about broadband internet. Nothing else is really important. So that's my perspective. Medium Earth orbit networks in this particular equatorial orbit only cover plus or minus 45 degrees. And for some reason, it's actually a bit of a wave pattern here. I'm not sure why it's a wave function, but if you look at the coverage maps, you're going to see here around 45 degrees, here around 45 degrees, going like that. Are we below 45 degrees here? What are we at, 40 or 42? What's our latitude?
39.
Yeah, 39. You don't get an equatorial MEO service. You wouldn't get it here in Bellevue. Oh well. Anyway, to cover the Earth in this particular orbit, you need 8 satellites. And I say this thing the receivers must track, because these satellites are going around in a circle. So your dish needs to follow the satellite. Right, O3B networks were the pioneer of MEO for broadband. They're focused on carrier and enterprise. They have an expensive service. The starting point is around $1 million a year to be a customer of O3B. But this is reasonable if you have no other options. MEO orbit, Ka band, look how tiny those antennas are. Like, here's the engineering technicians here. Go back and look at Sky Muster. Here they are here. Holy cow, look at that. Each one of these little dishes gives you 1.2 gigabits per second in a beam that has a diameter of 700 kilometers. Data communications only go up and down. There's no cross-linking between the satellites. Each of these satellites, 1.2 times 10, I guess. So we've got like 12 gigabits per second. 1, 2, 3, 4, 5, 6. Yeah, 10 of these are used for terminals to satellite, and 2 of them are used for downlinks to Earth stations. So we've got like 12 gigabits per second of capacity here, and that same 12 gigabits per second of capacity here for the downlink. By the time I wrote this slide, O3B had 144 gigabits per second of service online, and it ordered 96 more. I have a feeling we're up over 200 gigabits per second of capacity. Now this is really cool because a lot of the C-band satellite connections Pacific Islands were using 5 years ago were only 2 or 4 megabits per second. I visited Niue in 2016. Niue had just the week I visited upgraded from 4 to 8 megabits per second. O3B, the starting point, is 155. They don't let you buy lower. So when islands have gone from their reliable, hideously expensive C-band to O3B, they've typically increased their connectivity by 2 orders of magnitude. Unfortunately, they've taken the reliability down just a little bit, which makes everybody miserable. Anyway, O3B is super cool. On the ground, you have 2 tracking antennas, usually a couple of meters, like a 2.4 meter antenna, and the way it works is you've got one antenna that's always locked on to a satellite as it's going overhead. And the second one is hunting for the next satellite to come over the horizon. As soon as that next satellite comes over the horizon, the second one locks on. And then for people who are network engineering people, a crazy thing happens called BGP. And the routes just flip over from one satellite to another. You'd think they'd do something smarter than that, but whatever. O3b has rain fade even with 4-meter dishes. They're getting around this with having multiple earth stations on islands linked by fiber. Now, I told you there was somebody with some crazy ideas about earth stations and linking them together with fiber. These guys are talking about space lasers. They have planned a network of space lasers. NASA has done some communications via laser Earth to space at, I think, nearly a gigabit per second. I read something about 600 megabits pretty recently. These guys are talking about 100 gigabit per second optical satellite links with cross connects at 400 gigabits per second, again optical. Now, using optical to cross connect between satellites, great idea, it already works. Google are doing optical cross connects between their loon balloons right now. How successful they are at it, I don't know. I tried to buy some of their lasers recently. They wanted a lot of money for them. Anyway, laser light is a planned software-defined optical network intended to integrate with terrestrial networks as a low latency path that will be available 95% of the time. 95. And to get their 95% availability, they're expecting to put tens of downlink terminals in each metro market, link them all together with fiber, and hop around to find the one that doesn't have any clouds. They have done some crazy statistical analysis on their target markets, and they've said we can make this work 95% in the following cities. Now, why is this attractive? This is attractive because it will be the fastest intercontinental link. Faster than fiber, faster than submarine fiber. Because light through a fiber optic cable only goes at 2/3 of the speed of light. Light through the air goes at the speed of light. Submarine fiber optic cables, say from Los Angeles to Sydney, they don't go in a straight line. They definitely don't go in a straight line. Light definitely goes in a straight line. Does not significantly. So, who wants this? Stock traders. Who wants this? Militaries. Why do they want this? Because it's really easy to tap a fiber optic cable, and it's really, really freaking hard to tap a laser beam through free space. I mean, what can you do? The beam width is so small, you basically have to be at one end or the other, like so close to the actual receiver and transmitter that someone would know that you're tapping it. What else are they going to do with these things? Well, since these beams are steerable, they do expect to be using them to feed drones, high altitude aircraft that run above the clouds, other satellites, low Earth orbit satellite networks. Really, really, really neat idea. 19.2 terabits per second between each satellite. Huge, huge, huge amount of capacity. If they get this thing off the ground, so to speak, it will be really brilliant. Okay, into the last bit, the home stretch for this talk, low Earth orbit. Now, we have had low Earth orbit for a very long time. talking 1999 for Iridium, might have been up there in 98, launched in 99. Global Star, Orbcom, all these are low Earth orbit networks. If you have a low Earth orbit network, generally you will have global coverage. It is possible to build regional networks, but the way these orbits work, they're polar. So if you have coverage over North America, you're also going to have coverage over whatever's directly on the other side. I don't remember anymore. I do remember that Wellington, where I live, the antipode of that is in Spain. They have good wine in both places. That's what's important. You need tens of satellites for low Earth orbit. Today, it is only narrowband, but it is absolutely the next space race. OneWeb. The guy who founded O3B Networks left after a few years. O3B is now a part of SES. SES? Okay, thank you. I see a nod there. SES completed their acquisition in like April 2017, something like that. SES is a huge company with a lot of satellites, a lot of assets. Greg had left O3B before that. He founded OneWeb, and on the strength of his previous success, he's gathered more than $1.7 billion in venture capital for this project. The entire project could take $4 billion for its first iteration. Now, this is very different from the other networks. Here we had a satellite that was like a ton, maybe. Here we had SkyMuster, I believe SkyMuster, six metric tons for this one here, and O3B is 450 kilos. Getting into OneWeb, we're talking about satellites that are going to be 150 kilograms each. That's like, it's like a person-sized satellite. I don't know how much the CubeSats we were looking at before weighed, but I imagine a 6-unit CubeSat probably weighs 10, 15 kilos, maybe more. Could weigh more. Yeah, about that? All right. So we're looking at something that's like 10 times a 60 CubeSat, 60 liters, something like tiny, tiny satellite. 1/40th of the size of the SkyMuster. They're going to put 700 or more up in the air in 20 polar orbital planes. Each satellite is going to have 6 gigabits per second of capacity. So that's a 4 terabit per second satellite broadband network. Now, KU band, which is fantastic because it has better performance than KA. But where are they going to get all of this KU spectrum from? Because KU band spectrum is super, super occupied by television broadcast things around the equator. What they are going to do is something they're calling, I don't even have it on the slide, something they're calling progressive pitch. They're going to, as the satellites fly north and south, change the angle of broadcast of their beams so that they don't interfere with existing KU band users at the equator. They're going to reuse KU frequencies that are already in use. They're just going to use them in different places. Because if I'm sitting here in Valdivia and I'm aimed at a satellite for TV, I'm pointing like this, that same frequency can be used for broadband as long as it's not up there, because I've got this nice high gain antenna that's rejecting that signal from anywhere else. I'm just looking for it here with my television. So they're going to reuse a KU spectrum just by changing the angle.
Is it practical to have moving antennas for home users? Absolutely not. So one of the other technologies involved in OneWeb is the idea of beam steering subscriber antennas. Big arrays of antennas, printed arrays of antennas that will be electrically steerable for receive and transmit. Really cool stuff. So that's OneWeb. Now we get another, I am going to talk about 3 of the 7 proposed LEO broadband networks. These are the 3 that I personally think have the best chance for commercial success. Second one here is LeoSat. LeoSat is a European venture partners with Thales Alenia Space. So they're aligned with a rocket ship company. Let me step back here. OneWeb has been very, very astute with their partnerships. They're using Airbus to build the satellites. Airbus does that. Airbus is an investor. They're using Boeing to do networks and satellite stuff. Boeing already does this. They're using Virgin. Virgin's an investor, and they plan to use Virgin Galactic to launch their satellites. They plan to use Richard Branson's 747 to do aerial launches of their satellites. So they're going to fly the 747 up with a rocket strapped to the bottom. They're going to drop the rocket. The rocket is going to push the satellite into low orbit. This is much more efficient than launching straight up from the Earth and then using propellant in the rocket to move your satellite to the correct polar orbit. Here with the plane, you get almost all the way there, you drop it, it goes right into space. So one of the reasons I think OneWeb will be successful is because they've aligned themselves and taken investment from satellite manufacturers and a guy with a rocket ship company. So score. LeoSat has done the same thing. They have taken investment from Thales, who will launch their rockets. LeoSat doesn't care so much about how much it costs to get their satellites into space because they're only going to do 78. Only 16 gigabits per second per satellite, so a lot less than the big GEO satellites, a 1.2 terabit per second network, but I feel like they're using the Paris Metro principle for pricing. There is an amazing academic paper by Andrew Ogwischko from AT&T Labs, maybe 15 years old now, called the Paris Metro Pricing Principle for Internet Connectivity. Paris Metro at the time had 2 different lines. Technically and coverage-wise, they were exactly the same. They just priced them differently to deal with congestion. Higher price automatically meant less congestion. No other change. Lower price meant more congestion. And people who valued lower congestion would pay more to get the same thing. So here we have LeoSat, similar technology to OneWeb. They're going to sell a much smaller network that does almost the same thing, and they're going to charge like 10 times as much for it. And as a result, only business users are going to use this network. They're going to get committed capacity. It's going to be lightly used. Everybody's going to be happy. They're going to laugh their way to bank. LeoSat is intended for, in particular, banks, governments, any organization that needs a reliable connection between continents, between offices on continents that cannot be interrupted by an adversary. In New Zealand, we are very exposed. Our cable connections to the internet, 3 years ago, we had 1 cable. And that was the state from 2001 until 2015. 1 cable, Southern Cross Cable Network. It's two entries, but it's still 1 cable system. Now we have 3 cable systems, but there are a lot of places in the world that are restricted to 1 or 2 cable systems
Or even if they have a lot of cable systems, they come into a small number of points. The points are controlled by government. These guys are going to provide a network that gets around that. And so people will pay more. Companies, governments, spy organizations, whatever, will pay more to get their bandwidth. And of course, optical cross-connect. And throughout this network of 78, they plan to offer any one point on Earth to any other point on Earth at a super low latency. So that's LeoSat, 78 satellites, OneWeb, 700 satellites. Last one we'll talk about is SpaceX. SpaceX, Google, planning for world domination from it's Elon Musk, okay? I mean, it's gonna be world domination. Starting with 4,425 satellites. Starting because they've had additional filings with the FCC planning a few thousand more satellites. Like, I don't even know how many more thousand. Let me tell you this today, or today, a year ago, when I wrote this slide, there were 1,459 satellites in orbit for communications. There were fewer than 1,500 comm satellites in orbit. Today, 1,500 probably. This guy's gonna have one network with 4,500 to start. 20 gigabits per second for satellites, 1 gig to end users. So your end user bandwidth is going to be 1 gigabit per second. It is going to be Ka band. So how's that going to work? It's going to work terribly in rain. They're serious. They've got test satellites in orbit already. They've already launched a couple of the platform that they plan to use. They've had them in orbit since like last December. So I expect that they're just mass manufacturing these things, and sooner or later, we're going to see the first launch of, say, 40 or 50 of these satellites at once. Up in the sky. Crazy, crazy stuff. Now, I mentioned V-band briefly back here, and we're hearing a lot about V-band and LEO networks because all of the new LEO network filings that I read from earlier this year were for V-band. But none of that is going to be used for terrestrial connectivity. Optical cross-connect between satellites is really cool, really effective, really fast, and potentially really unreliable, because what do you have to do for two moving objects to track the laser beam? You've got to mechanically steer the beam. You've got it on a gimbal, and you're just going, you know, moving the thing around, tracking the laser beam. Motors, bad idea in space. Bad idea anywhere. Seriously, moving parts, bad idea. V-band allows you to beam steer, electrically steer your antennas. So for cross-connect between the SpaceX satellites, they had plans to do optical, but more recently they've said, actually, we might use V-band. We might use millimeter wave arrays of antennas. You can get like 256 elements at millimeter wave printed in an area this big. And with a very small amount of power, you can cause a beam to steer like across a 120-degree arc or better. So V-band, very popular, 60, 70, 80, 90 gigahertz cross-connect, probably between about 45 and 90 gigahertz is going to be used to cross-connect these things in space. So that's super exciting stuff. Really, I just love reading about it. Anyway, we have a few other things that are going on with broadband in the sky. However, it's all just sadness and disappointment. We have Titan Aerospace, which was purchased by Google in 2014. And the first time I gave this talk was in January of 2017 at an operators conference. And the day before I gave the talk, Google shut down Titan Aerospace. The idea was a solar-powered drone with some communications pods using the same sort of radio spectrum as satellite. Now we have Google Loon, which is still alive. Somehow the project refuses to die. They are using optical cross-connect between their balloons. It's a crazy ad hoc mesh network of optical mesh. They're using 4G spectrum borrowed from network operators to provide end-user service. And as of now, they were doing something in Peru. They did some recovery for some floods in Peru last year, and they moved the network over to Puerto Rico after the hurricane in Puerto Rico provided people with handset level coverage from the balloons. You know, another platform, Facebook Aquila, Facebook's thing, another one of these solar powered drones that was meant to go up and fly around for a few months at a time. Facebook canceled that project a couple months ago. Apparently they have given or sold the technology into some Airbus subsidiary, so there may still be an Airbus sub-company looking at these drones. But in all honesty, when faced with this, all the satellites in this photo are red. So like in my display, I've got like thousands of red dots, and here's, you've just got the blue label. Just imagine red dots all over this photo. See this link? It's not going to nothing, it's going to a red dot right here. Faced with a deterministic satellite network for which you can easily plan coverage, why would you operate a non-deterministic network like these frickin' meshy balloon things that are being blown around by the wind, or a drone that has to deal with weather systems and has mechanical properties because it's moving through air, has moving parts? Why would you have something with moving parts when you could have one of these guys that just goes up there and whizzes around until it gets hit by a piece of space junk, you know, and has its 5-year happy life, and then replace it with another? This seems to be the least costly, least complex way of getting broadband to the globe. So that is it. Sandra, I've done it. That was 1 hour and 30 minutes.
Yes.
Bingo. Thank you all very much.